Hi, my name is Lori, and I'm a support engineer with Geoslope. I've created a series of getting started tutorials for new users to Geostudio. So if you're brand new to using the Geostudio software and you're not quite sure where to start, then you've come to the right place. These tutorial videos have been designed to help walk you through the basic steps of creating a simple model using Geostudio. The main topics that'll be covered in this series will be how to use define to set up a numerical model, using the solve module to compute the numerical solution, and how to use contour to view the results and to gain a deeper understanding of the problem you're modeling. You can pause, stop, fast forward, or rewind these videos at any time by using the controller bar positioned at the bottom of the window. If English is not your first language, you might find it helpful to print out a copy of my script, which is available as a PDF from our website. So let's get started. AirW is always used in conjunction with either TempW or SeepW, finite element programs that are also a part of the Geostudio product line. It's a specialized program that allows for a wider range of geotechnical problems to be analyzed. For this Getting Started lesson, we are going to conduct two analyses. The first will be a SeepW steady-state simulation to determine how much water will flow into a tunnel that's located below the regional water table. The second analysis will illustrate how much water would flow into the same tunnel if the air in the tunnel was pressurized to 50 kPa. It's assumed for this tutorial that you are already familiar with the Geostudio environment. If you've never worked with Geostudio before, you may want to first review the Getting Started tutorial for SeepW. Here is the SeepW analysis without air pressure that has already been sketched. The units have been set to use length units of meters and time units of days. Under Key and Analyses, you'll notice that we are just doing a steady-state seepage analysis, so the airflow option is initially not going to be selected. First, let's draw the geometry region and include a circular region that will represent the tunnel. Circular regions are drawn directly over top of existing regions. Now we can define the material properties. For this simulation, we're going to make use of the soil property sample functions included in the software. To use these functions, you first have to create a volumetric water content function using the Estimate button. Select one of the sample functions available and type in a porosity value. Once the volumetric water content function exists, you can then estimate the hydraulic conductivity function. For this simulation, we'll use the Van Genuken estimation method. You will need to define the saturated hydraulic conductivity and the silty clay's residual water content, which was 0.05. For the first analysis, an air conductivity function is not required. The boundary conditions for the SeepW analysis include a total head of 16 meters, representing the regional groundwater table, and a potential seepage face around the tunnel, so the water can run freely into it. Now let's draw the mesh properties. We'll use a global element size of 1.1 meters. And we'll draw a flux section around the tunnel, which will tell us the total amount of water that will flow into it. The analysis has now been completely defined. In addition to the new AirW program, a powerful new feature in Geostudio 2007 is the ability to run many different analyses within the same project file. The geometry is considered project-specific. You can change boundary conditions, material properties, and even different types of analyses. Let's go back and set up a second analysis which will consider airflow, given that the tunnel has an air pressure of 50 kPa. Under Key in Analyses, add an AirW analysis to a steady-state seep analysis, and make it a sibling of the first analysis. Sibling analyses both have the same parent analysis, even if it's set to none. This time the airflow analysis option will be selected. Material properties and boundary conditions are considered analysis-specific, so we can change the material properties and boundary conditions assigned in this analysis. Let's create a second material for use for the AirW simulation. Since we still want to use the same volumetric water content function and conductivity function as the first material, we'll create a clone material and then just add the air conductivity properties. The air conductivity function can also be estimated from the volumetric water content function. A reasonable rule of thumb to use is that the dry air conductivity is approximately 60 to 100 times larger than the saturated hydraulic conductivity. We need to keep the same hydraulic boundary conditions as before, but we now need to add appropriate air boundary conditions. The air pressure of the tunnel will be 50 kPa, and the air pressure at the ground surface will be 0 kPa gauge pressure. Let's solve both analyses now. You can use the Control key to select both analyses in the Solve window so that they can be solved one after another. To view the results, click on the contour icon. The results that appear are for the analysis you were last viewing in Define, in this case, the one that included the air pressure. The blue line is called an isoline, and it can represent different parameters that can be changed using Draw Isoline. For this simulation, which used the pressurized tunnel, we are currently looking at the 0 pore water pressure contour, but let's change it to be the 0 matrix suction isoline. The definition of matrix suction is the pore air pressure minus the pore water pressure. Currently, the water velocity vectors are shown as red arrows and the air velocity vectors are green. You can make the vectors whatever color you wish for presentation purposes using Draw Vectors. Let's look at the contours. Right now, the contours that are showing are matrix section contours. The flux section label will tell us that the seepage in the pressurized tunnel was approximately 0.09 cubic meters per day. If we now switch over to the unpressurized tunnel results, we can see that the seepage into the tunnel was approximately 0.14 cubic meters per day, which is almost 40% more. The blue line in this analysis is the zero pressure contour, since the analysis only uses CW, and it assumes that the air pressure is set equal to 0. There aren't any matrix section contours, but we can draw pore water pressure contours. If at any time you need help with understanding a dialog box, you can click on the question mark in the top left corner to access the online help, or use F1 on your keyboard. You can also switch to the Analysis Start page, which has PDF copies of all the engineering books for Geostudio under the Documentation section. These books are very helpful in describing the features in the software and the theory behind them. You can also search through the examples database using specific keywords. When you're done, you can return to your analysis by clicking on the analysis list. We have reached the end of this introductory lesson. Not all of the powerful features of AirW have been used or discussed during the lesson. Specific details about each command are given in the online help and in the supporting documentation for AirW. Thanks for watching.